Hello again. What am I going to teach you today? I'm going to teach you how to count things. In particular, I want to suggest the question, how many different musical chords can you play? Suppose you wanted to just squash your fingers down on the piano and press either no notes or one note or two notes or all 12 notes at the same time. I'm not going to care whether we play the lowest copy of G or the highest copy of G, but just did we play a G? How many of those are there? Let's dig in. To begin with, we'll look at something famous from the Middle Ages known as Pascal's triangle, although its origins go way further back and its progressions forward go way further forward. Uh, it's related to a more contemporary piece of counting theory and statistics called Combinatorics and the binomial expansion theorem, fancy highbrow terms, but we'll see where it plays out. So let's dig in. So to begin with, let's talk about what Pascal's triangle is. Its formulation looks like this. It's fairly straightforward. You've probably seen it before. Do you know the rule that goes with this? Think about it for a minute. All right, well, the rule goes like this. Any two numbers side by side are added together and their sum is written below them. So an example here is 1 plus 2 equals 3. If this is just happening everywhere over and over and over again, and if there's a missing number, we treat it as a zero. So you might observe that, say, right here is another triangle we might look at. And we can say 0 plus 1 is 1. Or another triangle right here, where we can say 1 plus 0 is 1. So it's that same pattern, and it just grows downward organically forever. The next row would be 0 plus 1 is 1, and then 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is another copy of 10, then another copy of 5, and another copy of 1. So we might first observe that there's some symmetry hiding in here. Cool stuff with symmetry. It means if we get halfway through, then the other half is a freebie. We might look for other patterns in here. Of course, there's the obvious. We got the ones down the diagonal. Uh, but there's a few other patterns that are maybe a little less obvious. This one's still fairly obvious. We get 1, 2, 3, 4, 5. The next one here is going to be 6. So we get counting numbers down that diagonal. Of course, symmetrically counting numbers down this diagonal as well. The next diagonal is also important. These are what are called triangular numbers. And we get from triangular numbers bowling pin numbers. We get 1, and then we get 3, and then we get 6, and then we get 1 dot, and 2 dots, and 3 dots, and 4 dots gives us 10. Those are our triangular numbers. So they're going down there as well. And you can look for more and more patterns. And you might say, well, what kind of pattern might be 1, 4, 10? I don't know. Well, we could explore. We could look for it. There's a bunch of other patterns, and some of the other ones that I want to really particularly pay attention to. I want to observe what happens as we go across each row. In the first row, we just had 1, so the top, of course, is just 1. But in the second row, we get a 2 if we add them together. And in the third row, we get 1 plus 2 plus 1 is equal to 4. And in the next row, we get 1 plus 3 plus 3 plus 1 is equal to 8. Oh my. We're getting doublings, closely related to the octaves that we've discussed before, where we kept dividing things in half over and over and over again, and we got denominators that looked like 1 and 2 and 4 and 8 and 16. Right, here we get 1 plus 4 plus 6 plus 4 plus 1 equals 16. Nice. Okay, well, let's explore what these mean. I'm going to pick on this row because it's interesting enough but not so complicated that we can't brute force things at least a little bit. And I want to figure out where we're at in the schema and how far down we are. So I'm going to redraw things a little bit. I'm going to make a slightly different version of my chart where the addition pattern is perhaps a little less obvious, but now at least we have things in rows and columns so that I can label them. So I have my 0th row, my first row, my second row, my third row, my fourth row. I have my 0th column, my first column, my second column, my third column, and my fourth column. So we'll label these guys R for row and these guys C for column. And I want to be able to pick on a particular number in here and talk about where it came from. So that's the one that I'm going to look at here. And there's a notation I'm going to use for it. I'm going to say this 4 can be notated as 4 and 1 like this, where this first number here is going to be the row number and this bottom number here is going to be the column number. Kind of a silly looking notation, but that's what I'm playing with here. So pause for a moment and think about this second example right here and ask yourself, what would I want to do for this one? How could I write that down? And hopefully, oops, sorry for that. Hopefully we will all arrive together at 4 choose 3. That's the name we're going to give this. We're going to call this 4 choose 1. And this gives us a big hint of what exactly is this showing. So let me map out what this one is. There's something very special going on here, and I want to make sure that everybody can follow along with it by going not too terribly fast. I promised we'd talk about musical notes, but for now, I'm going to talk about flipping coins. Suppose that you had 4 coins you wanted to flip. How many different ways could you get 4 heads? How many different ways could you get 4 tails? How many different ways could you get 3 heads and 1 tail? So let's start making a list of those things. So 4 coins to flip. If we wanted to get 4 heads, we can get head, 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 head. And that's it. That's unique. There's only one way, right? It'd be similar for 4 tails. There's only one way for that as well. It gets more interesting when we want to think about what would it mean if we wanted to have 3 heads and 1 tail. How many different ways could that happen? Well, you could get your 3 heads flipped with the first 3 coins and the tail was the last coin. Or the first 2 could be heads, the third one tails, and the last one heads again. Or the tails could come on the second slot, or the tail could be the first coin. It's also worth observing at this point that I can think of this as flipping 4 coins at the same time and lining up the results consistently, but I could also think of it as flipping the same coin 4 times in a row and asking what happens with each flip. They're equivalent, so that's important to realize as well, that there isn't a difference there, but that they're equivalent. So this is what we're looking at this point. So we've gotten 4 there. Well, we described this as 4 choose 1 when we developed our notation, and we found the answer was 4. And that's exactly what this is saying. I have 4 coins I want to flip. I want to choose one of them to be a single tails. But we also saw that that was the same as 4 choose 3. That was also equal to 4. And this one is the same as picking, I want to have exactly 3 heads. And because it's a binary choice, if I pick 3 heads, that means I have to have 1 tail. Otherwise, it'd be a 4th head, and that's a different situation. So these two things are therefore equal to each other. So this is now explaining why we have this symmetry, why we can write it down either way and get the same 4 answers. And it's also showing us indirectly why this is also still the same question as this, fundamentally. To ask ourselves to get 3 tails and 1 head is still basically the same problem. We're changing our notations around, but it's still the same situation where the odd man out is just progressing through each of the different slots that it could potentially fill until we've exhausted every possibility, which in our situation is going to be 4. So this brings us back to the last piece right here. What about this 6? Well, this is what we call 4 choose 2. Because again, it's in the 4th row, but now it's in the 2nd column. And what would we call these ones? Well, this one over here would be 4 choose 0. And this one over here would symmetrically be 4 choose 4. These are going to correspond to picking deliberately that there will be no tails or 4 heads. And again, same thing. No tails amongst 4 coins implicitly means all 4 coins are heads. So those are also still always the same. That's the one way that we have over here. So what is this 4 choose 2? Well, this is telling us to figure out all the different ways that we could get 2 heads and 2 tails. And apparently that's the most common. There's 6 ways to pull that off. And it's a good, thoughtful experiment to brute force it and see if we can justify to ourselves why it is that. So let's see if we can make that list right here. So we could have 2 heads followed by 2 tails. We could have head, tail, head. We could have tail, head, head, tail. And what I'm doing here is I'm trying to be systematic about it. I'm leaving everything alone except progressing that one through. So I'm just kind of making a pattern on it. Now I'm going to take the same idea and say, well, what would happen if I started moving this other tail around? And I'll make a second column because I've moved that through its 3 slots. So maybe there's going to be 3 more. That kind of justify the 6. So I could theoretically move this tail over here. So I could have head, tail, tail, head. That would be leaving this one alone, and we'll put a triangle around this one, moving the triangle right there. I could theoretically put the triangle here and move the circle here, so that could be tail, head, tail, head. Okay, that got me up to 5. What am I missing? Aha, I have not tried tail, tail, head, head. Okay. So that gets me all of them. Gets me all my different variations there. And it turns out that there were 6 of those. So that's how that works. So what does this have to do with musical notes? Well, again, a lot of what I'm trying to get across here is there's a lot of things you can think of by analogies, whether we're looking at patterns that repeat themselves in other fields of mathematics, like patterns that we see in arithmetic and music at the same time, or whether we can come up with real life examples where things flip-flop back and forth, but they can have the same analogy, is all the same. And learning to think in these analogies is a fundamental mathematical skill. So coin flipping is an easy one we can think of, but coin flipping is just perhaps the most straightforward example of something that is just either or, a binary choice. And fundamentally, that's the same thing that happens with a musical note. Instead of thinking about there being so many different notes and how many different combinations, focus on one note at a time and say, I have 2 choices. I can either choose to play that note or not play that note. And if I choose to play that note, call that a heads. If If I choose to not play that note, call it a tails. How many different notes are there? There are 12. After all our chromatics in there are 12 notes. If we want to restrict ourselves just to our diatonic scale, our do, re, mi, fa, sol, la, ti, do, well, then there's 7 notes. Great, 7 choices. All we have to do is pick how many choices do we want to consider, and then we can consider which ones we want to play or not play. And if we get the full combination of all the ones we want to either play or not play, we've answered our question. So to keep the number a little bit smaller, let's consider our diatonic scale. So do, re, mi, fa, sol, la, ti. And we're not going to put do on there because we've already got do at the bottom. There are 7 choices. So this is going to correspond then to 7 choose however many we want. We could do 7 choose 0, which would be silence. The most underrated and most important part of music, the space between the notes and the rests and the rhythms and the timing is what makes music music. Without silence, there is no music. Just as without feasting, there is no fast, or without fasting, there is no feasting. 7 choose 1. That'd be playing individual notes. So one might argue if you're thinking about the formal definition of a chord that both of these don't count. And you could choose to take them off the list if you want. Silence isn't really a chord, and an individual note isn't really a chord either. So take them or leave them as you like, but they're in there. And then there's 7 choose 2. That would be a chord with 2 notes in it. And 7 choose 3. Oops, I like to make my fraction mark by accident there all the time. That would be a triad, 3-note chord, the most common. So you could say, well, how many 3-note chords are there? Great, the answer is right there. Then we have 7 choose 4, 7 choose 5, 7 choose 6, and 7 choose 7. That one's fun too. This one is the kid playing on the piano. This is you press down all the white notes with your elbow all at once. Crunch. So that's everything. Right. So depending on what you want to define as a chord, you can pick or choose all of these. But what does it mean to add them all up? Well, we've actually already answered the question back here. If we take the rows, they always add up to these powers of 2. And it turns out that the index that we adopted down here is the key to unmasking that. 2 is 2 to the first, 4 is 2 squared, 8 is 2 cubed. In other words, all of these are 2 to whatever the row number is. So we are playing with row number 7 here for 7 notes. So 2 to the 7th means that there are 128 different ways that we can press down these 7 diatonic notes to get some sort of chordal type feature. If we want to take away silence, that would be 1. And if we want to take individual, that would be 7. Those are easy. So we could easily decide to take away 1 plus 7, and that's going to give us 120 multi-note combinations. There's the answer to our question. And if you're interested in any of the other of these values over here, all one needs to do is draw out Pascal's triangle to the 7th row, which we are very close to. So I will leave that as an exercise for you to see what we'll land at for those last few. Thanks for listening.